Now we are moving on to the most common charged particle accelerator type, cyclic radio frequency resonant accelerators. To distinguish between the different types, a special classification system was invented. The first principle of this classification was proposed by a member of the Soviet Academy of Sciences, Vladimir Wechsler, who divided cyclic radio frequency resonant accelerators into different types according to 4 parameters: either constant or increasing magnetic field, constant or varying beam orbit radius, constant or varying RF frequency, and constant or varying acceleration ratio. I will explain what acceleration ratio is using the example of a microtron. According to this classification, 5 main accelerator types stand out. The first one is a cyclotron of various modification. It has a time-constant magnetic field. With the time-constant magnetic field, the orbit radius grows when the beam energy is increased. Cyclotrons operate at constant RF frequency and at a constant harmonic number. All the electric parameters in the accelerator are constant. This is one of those accelerators that can work in an uninterrupted mode. Cyclotrons are used for heavy particle acceleration. Originally, they were built for proton acceleration. Nowadays, there are specialized cyclotrons for heavy ion acceleration. It is, to date, one of the most powerful sources of charged particle beams. The average beam power of a cyclotron may reach 1 megawatt. It is one of the most convenient accelerators for its various technological applications. The next type is the very accelerator described in Wechsler's first article, which was dedicated to the phase stability principle. I'm speaking about the microtron. It has a time-constant magnetic field. As in the case of a cyclotron, the orbit radius of a microtron also increases. However, unlike a cyclotron, the acceleration ratio of the accelerating field rises during the acceleration period. In principle, this accelerator may also work in an uninterrupted mode. Later on, I'm going to show an example of such an accelerator, including its parameters. This accelerator is only used for electron acceleration. The next accelerator is a synchrocyclotron, or phasotron. Its magnetic field is constant, same as in the first 2 accelerator types. Accordingly, the orbit radius increases. But in order to preserve the synchronism of the RF field and of the orbiting particles accelerated in the accelerator, the frequency of RF accelerating field is lowered during the acceleration process. As this accelerator works on an alternating frequency, its operation mode is pulse-wise. First, an acceleration of a beam with decreasing frequency takes place. Then, the frequency goes back to its initial value. During this process, there is a pause in the acceleration mode. Due to the pulse-wise operation mode, the beam intensity in such an accelerator decreases by several orders of magnitude compared with a cyclotron. Today, practically no one builds accelerators of this type anymore. Let's move on to the 2 next types of accelerators. According to Wechsler's classification, they were the synchrophasotron and the cyclotron. The modern classification combines them with a generic name, cyclotron. How is a synchrocyclotron, or in modern terms a proton cyclotron, different from an electron cyclotron? During the acceleration period, the magnetic field of any cyclotron increases. It is increased to the extent that the orbit radius remains constant. If the particle is ultra-relativistic and its speed doesn't change, meaning it equals the speed of light, then the high-voltage supply frequency remains constant. During the acceleration of heavy particles, the speed of which is lower than the speed of light, the revolution period changes in the process of acceleration, and it is necessary to alter the accelerating field frequency. The harmonic number in both the accelerators remains constant.